Hello there. In this video we're going to investigate how to solve equations that involve radicals and also inequalities that involve radicals as well, and which sometimes can be a little tricky for a variety of reasons. So just as a basic idea, we're going to solve basic equations starting with the most simple, such as the square root of x is equal to 5, and also how to solve equations such as the square root of x is less than 5. And we're going to slowly evolve these examples into the ones that are a little bit more intricate and sensitive to deal with. Alright, so just as we did with polynomial equations and linear equations before, usually the solutions to equations are definitely related to the solutions of inequalities. Typically they are boundaries of one another. So let's just start off with the basics of how to solve radical equations, just to get a familiar idea with some of the basic things that we need to know. So suppose we have the square root of x is equal to 5. So if this is the case, what we can do is square both sides. So x square root square is going to be equal to 5 squared. So clearly we see that x is going to be equal to 25. Namely, the square root of x is equal to, the square root of 25 is equal to 5. And that's the only number that has this property, right? So if you have something like the square root of x is equal to 0, again, of course, x is going to be equal to 0 squared, which is clearly equal to 0. And if we have the square root of x is equal to negative 5, then clearly, well, what we can do is square both sides again, right? Why not? Right, and we have this, right? So what does that mean? Well, that says, okay, the square root of 25 is equal to negative 5, right? So that's what this says. So 25 equals negative 5, question mark? No. Remember, negative 5 is the secondary branch of the inverse of the square relation, not the principal branch, right? So again, we have some issues here, right? All right, so this does not always work. And this is very clear. You can look at the graph, right? So if you have this curve, right, this is y is equal to the square root of x, and negative 5 is down here, right? So of course this curve and this curve do not intersect, right? So if this is the case, then x does not belong to the set of real numbers, at least, right? Remember that the square root of x is greater than or equal to 0 for all values x in the set of real numbers. So if we have the square root of x is equal to, say, negative 7, it's impossible for the square root to be equal to a negative number. So in this case, we have no real solutions. So keep these small little things in mind. So let's start looking at a particular example. So let's solve x to the 2/3 is equal to 1. So what I can begin by doing is cubing both sides of this equation. Why not? So that's going to give us x squared is going to be equal to 1 cubed, which is 1. So if x squared is equal to 1, clearly we have the square root of x squared is equal to the square root of 1, and we know that the square root of 1 is equal to 1. The square root of x squared is the absolute value of x, and we know that there are two solutions to this equation, namely 1 or negative 1. Now, do both of these solutions make sense? Well, we can take a look at the graph to verify. So remember, this is the graph of x to the 2/3. And if we draw a horizontal line like here, y is equal to 1, we have two solutions, right? Here and here. So this point corresponds to negative 1. This corresponds to positive 1. So it definitely works. If you're not too sure, you can always check the graph just to make sure that everything you have checks out. So let's evolve the equation into something a little bit more interesting. Suppose we have 2x to the 2/3 plus x to the 1/3 minus 1 is equal to 0. So what we can begin by doing is analyzing these exponents, because we should be able to see that this is almost a quadratic equation. So what I'm going to do is I'm going to solve this by substitution by letting u be equal to x to the 1/3. So if that's the case, then that means u squared is going to be equal to x to the 2/3, and then I can use these two and replace them with these expressions. So my equation then becomes 2u squared plus u minus 1 is equal to 0. So, by some careful analysis, you should be able to know that this can be decomposed into 2u squared plus 2u minus 1 is equal to 0, right? So this is how to solve quadratic equations. And then we can factor by grouping, giving us this, right? So clearly, the parentheses are the same, so we get 2u minus 1 times u plus 1 is equal to 0, giving us two solutions in the space of u, right? So namely, u is equal to 1/2, or u is equal to negative 1. So remember, u was equal to x to the 1/3, right? So let us replace back. So we have x to the 1/3 is equal to 1/2, and x to the 1/3 is equal to negative 1, right? So I'm going to cube root both sides. So x is going to be equal to the cube root of 1/2, and x is going to be equal to the cube root of negative 1, right? No, wait. So we should be cubing both sides, right? We need to get rid of the cube root, right? So we need to cube both of these, right? So we have x is equal to 1/8, and x is equal to minus 1. So these are my two solutions to my original equation. And we shouldn't need to go back and simplify because we have not violated any domain restrictions in these calculations so far. Alright, so let's look at the square root of x plus 2 plus the square root of x minus 1 is equal to 2. Before we start to solve this equation, I just want to make a couple of things clear. Remember, we're going to be staying in the real plane. So for this expression, x must be greater than or equal to negative 2, and for this, x must be greater than or equal to positive 1, right? Since both must be real numbers, in order to sum in order to get equal to 2, at least we're assuming, we need to choose the overlapping part of this region, right? So that means whatever x we get in the end must satisfy this. So x must be greater than or equal to 1, right? If we get something that violates this, that means it won't work, right? So just keep this in mind. So what I'm going to do is I'm going to get rid of these square roots by squaring both sides of this equation. So once I follow that, I'm going to have x plus 2 plus 2 square roots of x plus 2 square roots of x minus 1 plus x minus 1 is equal to 4. Right, and let's combine like terms here. So I have an x and an x, a plus 2 and a minus 1, and also a 4. Right, so that's going to give us 2x, 2 minus 1 is 1, and then I can subtract 4 if I want to. Let's see. Now let's just keep it here, plus 1. Then I have plus 2 square roots, x plus 2, x minus 1 is equal to 4. So notice I'm bringing these two things here. So the only way I can do that is if I'm assuming that x plus 2 is greater than 0 and x minus 1 is greater than 0. And we're mandating that also because we're assuming that x must be greater than or equal to 1. So this operation is legitimate. So let's see here. Let's bring everything over here. So then we're going to have 2 square roots of x squared. Let's see, 2x minus x is going to be x. Minus 2 is going to be equal to 3 minus 2x. Now I'm going to get rid of this radical by squaring both sides. Then we're going to have 4 times x squared plus x minus 2 is equal to 9 minus, let's see, it's going to be 12x plus 4x squared. So of course, depending on the numbers that you have at this stage, you may have a quadratic equation, so you may have two solutions. that come out of this expression. But pay close attention at least to this example. We have 4x squared plus 4x minus 8 is equal to 9 minus 12x plus 4x squared. So is this really a quadratic equation? No, because the coefficient of the quadratic is actually equal to 0, which is very, very nice. So I'm going to bring 12 to the left, so I'm going to have 16x. I'm going to bring 8 to the other side, so I'm going to have 17. So I have x is equal to 17/16. So I need to ask myself, is this greater than or equal to 1? And definitely 17/16 is larger than 16/16, so yes. So everything is okay. Right? Now, what if you need to check this, right? So we need to plug this back into the, so verify if in doubt, right? You can always verify just to make sure, right? So I'm just going to verify just for fun. So I have the square root of 17/16 plus 2 plus square root of 17/16 minus 1. Let's see what this is. So 2 is the same as 32/16, and 1 is the same as 16/16. So this is going to be equal to 49/16 plus 1/16. Everything's a perfect square, so that's wonderful. So I have 7/4 plus 1/4, which is 8/4, which is 2, which is the right-hand side of the equation I began with. So it works. So that's great. So now let's get into the discussion of solving radical inequalities, and a little bit more care needs to be made. So here's a claim, and I want you to answer this and see if you think this is right or wrong. So if a is less than b, then a squared is less than b squared. So take a moment to think about this. Is this always true where a and b are real numbers? So if you took a moment to think and just try a few numbers out, you should know that this is false, right? So easy counterexample for this, right? We can take, say, -5 is less than 3, right? This is clearly true. I'm going to square both of these numbers, so we have 25 is less than 9. This is false, right? So clearly this is not a true statement. So what about this? So let's assume a and b are both greater than or equal to 0. So if this is true and a is less than b, then a squared is less than or equal to b squared. So this actually is a true statement. Right, so we need to make sure that before we square and get some inequality like this, we need to mandate that these two things are assumed to be true. So let's look at an example to illustrate this. So let's assume we have the square root of x plus 2 is less than 3. So I need to make sure that both of these are positive numbers, right? So clearly 3 is greater than 0, no big issue there. Square root of x plus 2, always greater than 0 or greater than or equal to 0 for all real x, right? So both of these are true, therefore a is less than b. That means a squared is less than b squared. So I'm going to subtract 2 from both sides, so that means x is going to be less than 7. Now remember, in order for this to be embedded in the set of real numbers, we need to mandate that x plus 2 is a positive number. So that means x must be greater than or equal to 2, right? So of course these two things do share an overlapping interval. That means the solution must be the intersection of these two intervals, right? So x must belong to the intersection of 2 to infinity. So what is the intersection of these two intervals? So that should be very easy to see. So that should be 2 comma 7, not inclusive of the right boundary, right? So that will be the solution to this equation. So how can you test this via a graph? So our goal is to solve this, say, via graphing. So this graph is very easy to solve. That's just the square root shifted to the left 2 units, right? So over here somewhere. And 3 is somewhere up here, right? Y equals 3. And this is y is equal to the square root of x plus 2, right? So when is this curve less than that? So that's going to be this piece here, right? Open circle, close circle. And you can find that this number is, of course, -2, and this number here is 7. All right, let's take a look at one more example that is a little bit more involved. So that is x is less than the square root of x plus 3, right? So the first thing we need to mandate is that both of these numbers are positive if we want to jump to the square, right? So clearly x plus 3 is a positive number, right? Provided that x is larger than or equal to -3. So that's okay. But there's no restriction on that, right? Because if x is greater than or equal to -3, we can choose, say, x is equal to -2, right? No big deal. And then we can't square both sides of this equation to sort of get what we want, right? So let's just choose a couple numbers to sort of see why this equation is a little bit more trickier to work with. So let's choose 2. So 2 is less than 2 plus 3. So 2 is less than or equal to the square root of 5. Is this true? Well, we know 2 is the square root of 4, and square root of 4 is less than square root of 5. This is, of course, okay. What about 3? Well, 3 is less than the square root of 3 plus 3. And what is that, the square root of 6? But 3 is the square root of 9, and the square root of 9 is bigger than the square root of 6, right? So we get a contradiction here, right? So clearly we do have some problems that we need to investigate, right? So let's take a look at this equation in a very careful way. So we know that the square root of x plus 3 is always greater than or equal to 0, or greater than 0, right? So the square root of x plus 3 is always greater than or equal to 0. So if I were to choose any negative number here, any, not considering the parameters of that, of course, this will always be true. So I can say choose -3, right? -3 is less than this. -2 is less than that. -1 is less than that. And 0 is less than that, right? And all the numbers in between, right? Why? Because the square root is always greater than or equal to 0, right? And remember, the minimum value of x, right, that we're allowed to have is -3, right? So it's clearly true for x in the interval -3, 0, right? This is by the properties of square roots and the argument of the square root function. So now we can look at the other numbers bigger than 0. So now consider x positive. So let's go back to our equation. X less than x plus 3. So we know square roots are always positive, and we're assuming x is positive in this consideration. So if this is true, then that means x squared must be less than x plus 3 by our arguments from earlier. So if this is true, that means x squared minus x minus 3 must be less than 0. And now we're looking at a quadratic inequality. Right, so the coefficient of the quadratic is 1, so that means the parabola is going to be facing upwards, right? So we know that this is less than or equal to 0 on some open interval in between, right? Called, say, from x1 to x2, right? So our generic solution is going to be 0 to, or, so before we've already verified -3 to 0, union x1 to x2. So if we use the quadratic equation on this, we're going to find that x is going to be equal to -b plus or minus the square root of b squared minus 4ac all over 2a, right? So that's just going to be 1 plus or minus the square root of 13 all over 2, right? So we have two numbers. We have x1 is going to be equal to 1 minus root 13 over 2, and x2, which is going to be 1 plus root 13 over 2. So 1 minus root 13 over 2 we can find to be approximately equal to -2.61, and this value is definitely positive, and you'll realize why I don't care about that number in just a moment. So we already know that this is true for this, and we cannot go below -3. So let's look at this interval. So -3, we have 0. So we know everything in this region holds. And we have x1 hanging out over here, right? So where's x2? Well, x2 is going to be over here. And everything in between those also works as well, right? By this graph, we've already verified that, right? So therefore, we include all of these numbers here with an open circle there, since we want less than, not less than or equal to, right? So from this construction, we have that x must belong to the interval -3 to 0, union 1 minus the square root of 13 over 2, comma 1 plus root 13 over 2. And since this number lies within the interior of this angle, we can combine these and just write this as -3 comma 1 plus root 13 over 2. And that is the solution to x less than x plus 3. Anyway, I hope this gave you some thoughts on how to be very careful when analyzing the solutions of radical inequalities, and this analysis of course can be extended to cube roots, fourth roots, and so on. Hope you enjoyed.